Oops. Before we get to diffraction and polarization, we still have another video about interference in Chapter 37. Diffraction and polarization is in Chapter 38. Interference phenomena, we can't forget about thin films. In a thin film, you can have phase changes due to reflections. An electromagnetic wave undergoes a phase change of 180 degrees, or pi radians, upon reflection from a medium of higher index of refraction than the one it came from. For instance, on here we have a light ray coming in from, say, air, incident on some kind of material, maybe glass, and as it reflects, it will undergo a 180 degree or pi phase change. Kind of like if you had a string to a rigid support and you have an incident wave encountering that support. As it encounters support, by Newton's third law, for every action there's an equal and opposite reaction. As the string is pulling one way, the support pulls exactly opposite. And so whatever wave comes in is going to be pulled exactly opposite whatever it was doing when it came in, and it's going to come out reflected exactly 180 degrees reversed. Of course, there's no phase due to reflection if you go at a boundary from a medium of higher index of refraction to one of lower index of refraction. So say if we had light coming from the glass headed towards the air, if it were to reflect off that interface, there would be no phase change for that reflection. And the mechanical analogy to that is if we had a wave pulse on a string, but our support was free. It was free to move. So whatever the wave did when it came in, it was free to move. There was no reverse action of the support or Newton's third law on the support. It just did what it did. And then when it comes back out, it's going to look exactly the same. So no phase change for that type of reflection. So this gets us to interference in thin films. They're commonly observed in thin films. Examples are soap bubbles, oil on water, oxidation layers in antique glass, and metal oxide layers on ceramic glazes. Interference is observed due to the interaction of the waves reflected from both surfaces of the thin film. So we need some things to happen in order to see interference in a film. An electromagnetic wave traveling from a medium of index N1 to a medium of index N2 undergoes a 180 degree phase change or pi radian phase change on reflection if the second index N2 is greater than the first index N1. So if you're going from lower to higher, you will get a phase change. No phase change if you're going from higher to lower. If your first index is higher than your second index, no phase change upon that reflection. The wavelength of light, lambda sub n, in a medium where an index of refraction n is the wavelength out of that medium in a vacuum divided by the index of refraction of that medium, lambda divided by n. So we have to keep that in mind. If the light goes into a medium, the wavelength is going to be shortened by the index of refraction of that medium. And one of the reflected waves travels a greater distance than the other reflected wave. So we're going to have a path difference between the two interfering waves. So we have a phase changes upon possible reflections. We have a difference in wavelength if one wave is passing through a substance. And we have a path difference if we're interfering waves off of two different boundaries. Here's an example. We have ray 1 coming in here, and we have a reflection off this first surface A, and there will be a 180 degree phase change on that first reflection. Then the refracted ray goes through the substance, and as it's going through the substance, its wavelength will be shorter by the index of refraction of that substance. It will internally reflect off the second surface B. In this case, we're going from a higher index to a lower index, so there'll be no phase change upon that reflection. And it starts to come back. It travels an additional distance, though, equal to twice the thickness of the film. It goes there and back again, and with that shorter wavelength. So we have to calculate that into our phase change, because there could be a phase change due to what difference in cycles we have as the waves pass that extra path difference. All these we will consider into our thin film interference. So in this particular case, let's say we had a thin film. When light passes through a film of soap, which is exactly 3/4 of the wavelength of green light, we will get constructive interference for green light and not necessarily any kind of real constructive interference for any other color light, because the green light will pass an extra 1.5 wavelengths of path difference, and upon reflection we'll get a half wavelength from that. So we'll get an exact constructive interference of multiple wavelengths when it comes back out. That means we're going to see a nice green reflection from that thickness of film. Here's a soap bubble of varying slight thickness, and where the thickness is just right, 3/4 of the wavelength of green light, then you will see green. But if it's 3/4 of the wavelength of violet light, we'll see violet. And so that's why we see all sorts of colors, because the thickness of this thin bubble film is varying itself as the light is interfering with it. Here's some oil on some pavement, and we can see different colors there due to the varying thickness of the oil on the pavement itself. Not sure what this is, but we can see the different colors of the interference in this pattern. As we do the interference, the light you actually see off of a hummingbird is not necessarily the color of the hummingbird itself, but the interference of light due to the reflections on the hummingbird that gives you a specific color coming back towards you. If he wears a sweater, you won't be able to see this, but most of the time hummingbirds don't wear sweaters. All right, so path difference is important. To get constructive interference, since we already have one phase reversal for a thin film, we want the rest of the phase difference to be due to the path, and we want that to be a half wavelength difference so we can get constructive interference when we come out. So we want twice the thickness of the film, 2T, to be equal to an integral number of half wavelengths of the wavelength of the light within the film, within the medium. That's going to be lambda sub n. So that's going to be an integral number of half wavelengths. Lambda divided by n is our wavelength within the medium. So this translates to 2 times the index of refraction of the medium times the thickness is equal to an integral number m plus 1/2 times the wavelength of light in a vacuum. That will give us constructive interference. This takes into account everything. The difference in optical path length, the 180 degree pi phase change for a thin bubble film, which is surrounded by air on both sides, and the shorter wavelength occurring within the bubble film itself. For destructive interference, same ideas, only we want the total path difference to be exactly an integral number of wavelengths, and let the one phase change, phase reversal, do our destructive interference for us. So we want 2 times the index times the thickness to be an integral number of wavelengths that gives us destructive interference for the soap bubble. So this is a look at what the soap bubble might do, where we have one reflection, 180 degree phase change, the other reflection, no phase change. So going through a media surrounded by air on both sides, we would have one phase reversal and our formulas apply. But it's possible we could have a thin film on top of another substance. And so if we were going from air, say a lower index, to a thin film of silicon oxide, and then we go even to a higher index substance after that of silicon, then we would have a phase reversal every time we're going from a lower index to a higher index. So in this case, we'll have a phase reversal on our first reflection and a phase reversal on the second one as well. That's going to reverse our formulas for constructive and destructive interference. Because in this case, we want the path length for constructive interference to be an integral number of half wavelengths, and for destructive interference to be, we want constructive interference to be an integral number of wavelengths, and destructive interference to be an integral number of half wavelengths. So for interference with thin films, the equation to use for one phase reversal is 2nt equal integral number of half wavelengths for constructive interference, destructive for 0 or 2 phase reversals, and then just reverse that, 2nt equals m lambda for destructive interference for one phase reversal, and constructive interference for 2 phase reversals. Another way we can get interference from an idea of a thin film, in this case a thin film of air, if you will, is Newton's rings. We put a plano convex lens on top of a flat glass, and we let the air gap in between the two act as our thin film. So in this case, if I have a ray of light coming in like this, part of it will refract here, and that'll go through air, giving me a phase reversal when it reflects off the flat glass here, coming back, whereas this ray number 2 here is not going to have a reversal at all as it goes from a higher index glass towards air here. So we're going to end up with 2 rays coming back with one phase reversal, and hence the path difference will have to be a half wavelength to get constructive interference, and integral number of wavelengths to get destructive interference. So constructive interference would correspond to 2t m plus 1/2 lambda. Note that there's no index of refraction in this equation because the index, the film, if you will, is air, and the index of refraction of air is 1. So we have a thin film of air. It might look something like this. So we have this plano convex lens on top of a flat glass, and we see this interference pattern. The length between fringes is just showing us how it doesn't change much in its thickness as we're towards the curved part of the lens resting on the glass. But as we get further and further out and the thickness is changing more rapidly, then the fringes are closer together. Actually, this kind of pattern can tell you how good your lens is, because if you had a perfectly grounded lens, then you should have a perfect symmetrical pattern on this Newton's rings pattern. And if it's not symmetrical, then you want to go in there and shave off the lens so that you can create this pattern that's perfect, and then you know that you've created or you've worked your lens to the point where it is perfect. I want you to study this and take a look at this pattern really closely for these reasons. Study it very, very closely and tell me what you see. Keep on looking at it. Keep on looking at this pattern. You will study your physics. You will study your physics. I'm going to use any kind of teaching method I possibly can. Okay, CDs and DVDs. Data in CDs and DVDs are stored digitally. A series of ones and zeros read by a laser light is reflected from the disc, and that will give us either constructive interference or destructive interference depending on how they hit the disc, and that will give us a 1 or 0 or binary code. Strong reflections correspond to constructive interference. These represent zeros. Weak reflections correspond to destructive interference. These reflections represent ones, giving us our binary code. Here's how it might look. We have a laser light coming in. Some of it hits the pit here, and if we're on the edge here, some of the light will hit the top of this protrusion here, and that interference, the difference in path length between the two, if that pit depth is equal to 1/2 of the wavelength, there will be a path difference of 1/2 wavelength, and hence we'll have destructive interference corresponding to a 1 on our binary code. So every time you hit a interface here of the pit, you will get a 1, and anytime you're timing and you get nothing, you're either flat on top or flat inside the pit, you will get a 0. So as you're timing this, 0, 0, hit the edge, a 1, edge 1, 0, edge 1, and so forth as you go across the flat planes. And that gives you a code for recording all this digital data. So all the bump edges are recorded as 1s, all the flat planes are 0s. Same thing for DVDs. Difference for DVDs is they use shorter wavelength lasers, and hence your track can be smaller as well. So your track separation, your pit depth, your minimum pit depth and length are all smaller for DVDs. That allows you to hold more information on the same size disc. DVDs can store about 30 times more information than a compact disc or CD. You can also have dual layer or single layer. A dual layer has a transmissive layer that allows you to get double data off the same surface of the DVD. So it allows you to get data from one layer down below, and then you have reflections off the second layer, giving you more data to collect and to be able to store on the dual layer disk. You can go one better. You have Blue Jay technology. In Blue Jay technology, you shine the laser off a blue jay, and the interference phenomena of the wings of the blue jay help give you your pits, your constructive and destructive. Wait, it's not Blue Jay technology. It's Blu-ray technology. Blu-ray technology uses a different frequency laser. Blu-ray technology allows you to store even more information, get higher resolution, and store more information onto the disk. That concludes our second short lecture on interference phenomena. Try your hand at some of the problems in the problem.